Hello and welcome to this math video. In this video, we'll prove that the set Zn/Z is a field if n is prime. We'll do this by proving about 9 properties of this set, which show that it's a ring, and then showing the 10th property that shows that it's a field. I've already made a video about this set called modulo arithmetic. It might be a good idea to have a look at it before looking at this video. So this is what this set looks like. It's a set of all whole numbers with bars on the top going from 0 to n-1. The elements of this set are known as cosets and are themselves sets of numbers. There are an infinite amount of elements in each of these cosets, and each coset represents all of the integers that have the same remainder when divided by the number n, using long division. So we'll show some foundational things about this set. When we add two of these cosets together, it can be written out as these two numbers plus a multiple of n. And we can factorize this expression like this, so that the multiple of n is inside one bracket, and the sum of these two remainder numbers is in the other. We can then rewrite this coset as the sum of these two numbers under the bar symbol. It doesn't matter if this number is bigger than n, because any numbers with the same remainder can represent the same coset. This is multiplication in this set. We can expand this expression out by using the definitions of this set to give us this expression. Then we can manipulate this expression to give us this expression, where all of the multiples of n are gathered together inside this bracket. And then finally, we can reverse the definition of members of this set to give us this coset. We can use these results to prove that this set is a field. Now to look at a more concrete example of this set. If n was made equal to 7, then we get this set of numbers from 0 to 6 with bars on top. If we add these two cosets together, we get this when we expand out these terms. And we can gather these multiples of 7 together and add the whole numbers or integers together. And using the definition of these cosets in reverse gives us this as the sum of these two cosets. Here's another example. We can add these two cosets together. Expanding these cosets gives us this expression. We can gather the multiples of 7 together. Then we can add the integers together. We can get the smaller integer that represents this coset by splitting this integer into this sum of integers. We can gather the 7 inside the brackets. We can then use the definition of cosets in reverse to give us this answer. Here is an example of what the coset 1 bar looks like. It is all of the multiples of 7 with 1 added to them. And I included the set union symbol so that I could include all of the negative numbers that get larger in magnitude towards the other direction. So now to start proving that this set is a field, we'll firstly show that it contains a 0 element. Its definition is that adding 0 to any number doesn't change that number. I want to prove this using these identities that we've worked out earlier, and that make the calculations faster and easier. We'll start with this addition statement. Then we can put everything under the bar like this. And we can evaluate everything under the bar to be this, because they are all integers under the bar. So now we've proven that 0 bar is a left-hand 0. We can also similarly show that this is a right-hand 0 too. So now we've shown that this set contains a 0 coset. Now to show that a 1 is contained in the set. This is the definition of a 1, that any number that is multiplied by it, either on the right or the left side, is left unchanged. So we'll assume that the 1 is the coset called 1 bar. We'll multiply it on the left by another arbitrary coset, a bar, and we can bring them both under the 1 bar. And multiplying any integer by 1 gives us this integer back, unchanged. so we've shown that it is a left-hand one. And we can similarly show that it is a right-hand one as well, so we've proven that it contains a 1. Now to prove closure, that the sums and products of any two cosets is also an element of this set. We'll start with addition. We'll add these two cosets together. We can bring both of these integers under the bar to give us this coset. And because it can be written as a coset, then it is also an element of this set. So we've just proven closure for addition. We can similarly show closure for multiplication. We'll multiply two cosets together. Then we can bring both integers under the bar to give us this coset, which is in this set because it is a coset. Now we have to show that every coset in this set has a negative or opposite that can be added to it to make 0. It has to be both a left and right negative. So I claim that the negative of A is this coset, with a negative A under the bar. This is a big difference, because we are now saying what it actually is. Now we'll add this negative to the right side of A. We'll make this substitution. Then we can bring both of these numbers under the bar. We can add them up to make 0, because they are both integers under the 1 bar. So the right-hand negative exists. We can similarly show that this is also a left-hand negative. So we've proven that every coset in this set has a negative. Now we have to show that associativity is true. That means that this bracket swapping equation is true for every element of this set. The deeper meaning is that the order of addition operations doesn't affect the result. So we'll start with the left-hand side of this equation. We'll manipulate it so that everything is under the 1 bar. Then we can manipulate these numbers easily like this, because they are all integers. We can then manipulate every integer to be under a separate bar like this. So now we've proven this property. Now we have to prove the associative property for multiplication, which is similar. We'll start with the right-hand side. We'll manipulate everything to be under the 1 bar. We'll manipulate these numbers under the bar like this, because they are integers and can be easily manipulated. We can then manipulate this expression to be the left-hand side of this equation, thus proving this property for cosets. Now to prove commutativity for addition. It doesn't have to be true for multiplication, though it can be. We'll start with the right-hand side of this equation. It easily manipulates to be this using this property of addition we found earlier. We can easily swap these numbers because they are integers and not cosets. We can use this addition property again to get the left-hand side of this equation, thus proving this property. Now to prove distributivity. This property involves both addition and multiplication. We'll start with the left-hand side. Then we'll get all of the integers under the 1 bar. We'll manipulate these integers under the bar like this. Then we'll manipulate this equation to be the right-hand side, thus proving distributivity. We've now proven that this set is a ring, but we still need to prove one more property to show that it is a field. And so this is the final property that we have to show, so as to prove that this set is a field. Every coset in this set must have an inverse, and it must be both a right and left inverse. Since n is prime, we can use this property, that the GCT, or greatest common divisor, of a prime and any other number is 1. We can then use Euclidean's algorithm to state that this equation is true. We can manipulate this equation to be this. We can then transform this integer equation into this coset equation, and we can separate these numbers out so that they are under different bars. And so we can immediately find the inverse of A bar, which is X bar. that we found using Euclidean's algorithm, and x bar turns out to be both a right and left inverse. Thus we've proven that this set is a field, by showing that this set satisfies all of these 10 properties or axioms. So I hope that you have found this video helpful, educational and enjoyable. Please click like and subscribe if you did. Feel free to share this video with anyone you like to. Please leave some helpful thoughts in the comments, and thank you so much for watching.